The next section is diffraction. This is one of the properties of waves. Again, and discuss qualitatively the diffraction of waves at apertures and obstacles. So what we have to do is basically compare the size of wavelength and the size of the aperture. Let's take the first case. We have a fairly long wavelength compared to the size of the aperture. So the wavelength is of a larger size than the gap, the aperture. If you were to sketch these, you should know that since the medium is the same, the velocity will be constant, the wavelength will be constant, and the frequency will be constant. But what will happen is that as the wave passes through the aperture, this line here will be the same as any wave that was coming through anyway, but then it was to curve at the side. The smaller the gap compared to the wavelength, the more the curvature, and the closer to the boundary here the wave will go. This displays a great deal of diffraction. The wave, the energy bends round corners effectively, especially if it's a tight gap, a small gap with a long wavelength. Here, however, the wavelength is much smaller than the size of the gap. Most of the waves pass through unaffected in this area here, but you do see some diffraction effects at the edge of the wave. Remember, V is equal to F lambda. As long as the medium stays the same, the velocity will be the same, the frequency will be the same, and the wavelength will be the same. It's just that the wave will curve around a sharp edge or a barrier or an aperture. For example, if this is a plan view of a building, it is possible to hear the sound on the other side of the building. The wave front moves this way, and on this corner it will diffract around, and it will diffract again on this corner, so it is possible to hear it here. This is an example of diffraction. The sound wave bends around the building due to its corners. And here again, if you're standing here on the other side of a hill, you can hear this because the sound goes in all directions, but it will diffract around the top of the hill, so you can hear it here. Here we have radiation, very short wavelength compared to the size of the diameter. The wave travels straight through and there is very little, if any, diffraction. Here, however, the wavelength is much longer and it's larger than the size of the aperture, so you get a noticeable diffraction effect. The wave bends as it goes through, spreads out as it goes through the aperture. This is a bat. We know that bats use ultrasound to detect moths and creatures and to be able to navigate around. Why do they use ultrasound and not sound that we can hear? Nice bat there. Another nice bat. So this bat is a North American big brown bat which uses clicks that sound between 20 kilohertz and 100 kilohertz. On a warm summer night, what wavelength range does 100 kilohertz correspond to? Well, we know the frequency is 100 kilohertz. We know the velocity is 300 meters a second. And using the equation V is equal to F lambda, we rearrange to get the value for lambda, which gives us, so the wavelength is 3 millimeters. This means it is able to see objects with sound which have a wavelength, which have a size of 3 millimeters. Now, if they used a frequency which was 10 times as much, 3 centimeters, they wouldn't be able to see clearly where that object was, and they wouldn't be able to define it because they would have a long wavelength and the diffraction effects would be too much. With a very short wavelength, because of a very high frequency, the diffraction effect is minimal and you will get some reflection, and it will be able to determine precisely where the moth is, for example.